Hi guys, welcome to my new video. In this video I'll be showing you about AVL tree. So as all of you might know, AVL tree is actually a type of BST. So let's start explaining AVL tree with the help of this BST. So let's consider a parent number. This is the parent element over here. So let's consider a parent number like 10. Okay, and then the specialty of BSC is like on the left side and the number should be smaller than this parent element, and on the right side the number on the right side should be greater than this parent element, this 10. So on the left side let's consider another number like 7 and which is lesser than 10, and on the right side let's consider another number like 15 which is greater than 10. And in the same way let's write another number on the left side of this 7 like 5 which is smaller, just like the previous two, and on the right side let's take another number greater than 7 like 9. Okay, the same thing happens over here also. So on the left side it's a 13 and on the right side it's an 18. Now this is a perfect BST, like which is an AVL tree. Okay, now you might be thinking what's the difference between BST and an AVL tree. Okay, I'm gonna explain that now. So over here everything looks fine, everything looks balanced, neat, clean, except for my handwriting. Everything looks fine. And then what if I draw an extra node like this on the left side? What happens then? It's like if I draw 3 over here just like this, now it feels like it's not that correct, right? Because it looks something different, like it doesn't look neat. So what if I add one more node? Like let's add one more node over here, and then blah 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 blah. Okay, and then let's add a number. Since it's on the right side, let's add a number like 4. Okay, now this 4 is greater than 3, but then if you look the whole thing doesn't look good. So now actually we have added impurities. This impurity is called the unbalancing factor. So like if you take 18 over here, there's nothing on the left side or right side, so the balance factor of 18 is 0. And it's the same over 9, it's the same over 9, 13 and 9 and 13, because there's no other element branching from there. And it's also the same over 4 because there's no other element below that. So all of them have the same balancing factor called 0. Well, the balancing factor of 15 is also 0 because there's one over here like 13 and another over the right side called 18. So if you consider one element is over right side minus another element over the left side 1, so 1 minus 1 gives you 0. So it is 0 over here. It's the same over 7 also, because on the right side we have got one element 9 and on the left side we got another element 5. So when we subtract the number of elements on the right minus left, like 1 minus 1, 1 minus 1, we get another 0 over here. So we got another 0. And then in the parent also, the root element 10. Here also on the left side we got 7 and on the right side we got another element 15 to compensate the 7. So the balance factor is 0, but it all changes over 5 and 3. So if you take 5 over here, we got 1 on the left and we got nothing on the right. So the magnitude of the balance factor will be 1 regardless of the sign, even if it's minus 1 or plus 1, because some people take the left side as minus 1 and some people take the right side as plus 1. So if we take left side as minus 1, then the balance factor of 5 is minus 1. Okay, now if we are taking 3 to find the balance factor of 3, we are looking on the left side, there's nothing on the left side, so it's 0 plus when we look at the right side we got 4 over here. Since there's one element on the right side, we give 1 over there, so 0 plus 1 gives you 1 over here. So that is the balance factor of 3. So this is how you find the balance factor. So if you take 3 over here, 3 over here, the balance factor of 3 will be the balance factor of right side minus the one on the left side. So we got 1 over right side, so we can consider that as plus 1, and then we got nothing on the left side, so what we get is 0 plus 1, which will be 1. So the balance factor of 3 is 1. Similarly, when you check the balance factor of 5, we'll consider what is on the left side. There's one thing on the left side, so you got 1 over there, and you got minus 1 over there, plus you consider what is the number over here into negative 1. So but if there's any element on the left side, you have to multiply it with negative 1 and then add it over there. So we add minus 1 again from the left side, and then you get there's nothing on the right side, so the balance factor from the right side, the contribution from the right side is 0. So the balance factor of 5 will be minus 1 plus minus 1 is equal to minus 2. So this is the balance factor of 5. So this is where we need the application. The AVL tree happens. Like in this case, when the balance factor of 5 is minus 2, or when the balance factor of any node was greater than minus 2, we try to make changes in it such that the tree will be back again in this form, so that there won't be any other element over here which can create a high difference. Even if it creates a high difference, it can only create a high difference of just one element, not more than one. So that is the AVL tree.
Okay, so let's consider a BST like this, so that the root element be 20, and as you know, the element on the left side should be lower than the parent. So here, as 20 is the parent, the element on the left side, it should be 17. Okay, and let's take a number 17, which is lesser than 20, and it's kept over here. Now we need a number greater than 17 but less than 20, so we are keeping a number like 19 over here. And then just like what we have done over here, we are keeping another number lesser than 17 over this part. And then let's take 15 over here, and a number smaller than that over there, and then another number smaller than that, and like that. We have given all the numbers over here. Okay. Now what we have to check is the balance factor. So for converting a BST into an AVL tree, the major thing is balance factor. If as you recall, if the balance factor is greater than minus 2, or if it is minus 2, then only then we have to change the BST, otherwise it is already an AVL tree. So let's check the balance factor of 19 first, because it's the like it does not have any more branches. So if we check the balance factor of 19, it's going to be 0, because there's no right element or left element. Now if you take 12, the leftmost element, then still it does not have any more branches, so its balance factor should be 0. Now if you take 30, it has just one left element, does not have a right child, it only has one left child, so its balance factor should be minus 1. And for 14, it only has one left child and no right child, and its balance factor is minus 1, so it adds up and it becomes minus 2. And so it gets adds up again, and it becomes minus 3 over here, and at 17 it becomes minus 4, and at 20 it is minus 5. So now we are going to change this. Like we are not gonna regard the parent element, I'm gonna regard this element and then make some changes in this. So let's try to sort this part of the program. Let's try to sort this part into an AVL tree. So For that we have to at first take this much elements outside, and then we have to sort it out. So at first, in this case, like for making it into an AVL tree, at first we have to balance this element. So for that, we have to take 15 on the right side of 14, as 15 is greater than 14, and 13 and 12 is lesser than 14. So we're gonna attach this 14 in place of 15 over here. So we'll do that, and then now we have got 15. So since 15 is greater than 14, we're gonna keep it on the right side. And then now we got 13 is lesser than 14, so we are keeping it on the left side. And now we have got 12, which is still lesser than 13, and we are keeping it on the left side. So how did we do this? I'll show you again. Like in this case, we know it is clearly unbalanced. So in this case, we are doing a right rotation such that this 14 comes over here and the 15 goes over here. So in the right rotation, the whole element moves rightwise in a circle manner. So at first we are trying to make a copy of this element over there. Okay, and now we're gonna do the cycle by replacing this 14 in over here and this 15 over here. So when we replace this 15 in this side, this 14 will be attached to the 17. So we take that, and then after that we got 15, and then we connect this 13 and 12 over here. Okay. This is how you do one rotation.